Hi, this is the second set of lessons on indefinite integration, and we should expect one more of these. The lesson we're doing today is called U-Substitution. This is a method of integration that allows us to undo the chain rule. So the notes I've got start off with asking you to remember the function composition feature that you maybe were taught in Algebra 2 and probably did some more practice with in pre-cal. The idea with function composition was we had g of x inside of f of x, and we were using that function notation, those symbols that mean function f of x and g of x, to then write an equation based on what they were specifically listed as, this cube root of x and the 2x squared plus 1. So if we were going to compose g inside of f, then we would write the outside function, the cube root of x, whatever was an x, and inside of that we'd have 2x squared plus 1. So what used to be underneath that cube root was x, and we replaced that with g of x. So we put the output of one function, the 2x squared plus 1, into the input of the other. So this idea is going to be really critical for learning U-substitution and working through the procedure for integration. Now, the idea with U-substitution, like why we even use it for integration, is we can deal with something like what's given here that I'm boxing in orange. We can deal with a binomial squared times another variable. We'll just multiply it all out. We'll end up with this trinomial, and then we can integrate each piece individually. And you can see the answer there at the far right. But with something like x squared minus 5 to the fifth, or minus 1 to the fifth, that is going to be a pain in the butt to multiply out. So we aren't going to take a traditional method of integration that we've learned so far. And it gets even worse if that fifth power on that group was all of a sudden maybe a fifth root or another type of grouping function that we don't know how to integrate. So we need to use U-substitution. And U-substitution is gonna be what undoes the chain rule. So I put a little reminder of the chain rule there. You don't have to write it if you remember it, but basically what it does is it takes the inside function of a composition of function and an outside function of that composition of function, so f of g of x, and it can take the derivative of that thing. So if you don't remember it, it's listed right here. But we're actually going to integrate the function given in that little bit of text above. So we're going to try integrating that x times x squared minus 1 to the fifth. So the big deal with U-substitution is we define U. And defining U is going to help us make our integration problem an easier process. And that's because we need to somehow create this situation, the chain rule derivative. We need to see the chain rule derivative in, I know I'm underlining a lot of things right now. We need to see the chain rule derivative in the integral in order to then put it back to just a composition of functions. So once we see that derivative, then we can get it back to a composition of functions. So defining U is all about seeing it. So U should be the function inside a group. So we're going to say u is equal to x squared minus 1, because x squared minus 1 is clearly in the group of something to the 5th power. Okay. The next step is to find the derivative of u with respect to x. So we're going to take the derivative of what we just defined. So they're going to build on each other. So if I take the derivative with respect to x of u equals x squared minus 1, then that's going to be equal to du over dx, that's the derivative of u with respect to x, is equal to 2x minus nothing. So 2x is just the derivative of u with respect to x. And that makes sense because 2x is the derivative of x squared. And now we're going to solve for du because we are going to need it to substitute eventually. So I'm just going to write du equals 2x times dx. So you can see I've multiplied both sides up here by dx. So times dx times dx. And that's just to get du alone. Now, I'm doing all this so that we can substitute, that's why it's called U-sub, our u and our du into the problem. So we are going to look at what our problem is saying. So our problem is saying we have, let's see, we have substituted, we have found out what, well, we've defined u, and we've sort of found, so here's u, let me highlight that in yellow on what we wrote. So here's u, right there. And we've sort of found what dx times x is. It's right here as well. It's what we found from our derivative. So this method is going to have us replace everything in the original function with what we do to set up the chain rule derivative. So we see that we almost have exactly what we need to match du and u inside of our integral. So in fact, I should add something here. I should say balance for integration. We need to balance our du equation so that it looks exactly like, so that this right side looks exactly like x times dx. So we're just going to divide both sides by 2. So 1/2 du is equal to x times dx. And now that we have exactly what we need on this right side, we can effectively replace what's in our integral with what we found. So I'm going to replace x times dx with 1/2 du. So I'm going to do 1/2 times du, and then I'm going to have a group to the 5th that can stay. That's not a big deal, and I'll show you why in a second. I'm going to replace the x squared minus 1 with u, and then I'm going to rewrite this a little bit so it looks like more of a normal integral that we can actually deal with. So the integral of 1/2 u to the 5th du. Now, hopefully you can see why this helps us with the derivative. We have substituted everything we need into, and I'll show you what it all looks like. We've substituted everything we need into this integral so that it's actually manageable and we can do it with old rules that we already know from integration. Excuse me. So we can now integrate this. And I'm sorry I'm working sideways, but the integral of u to the fifth, 1/2 u to the fifth, is 1/2 times 1/6 u to the sixth plus c. So 1/12 u to the sixth plus c. And that's gonna be our integral. We just have to put x back into this this substituted answer so that we have the integral of that. So I need to go back and remember what I replaced with what. And the only thing we have to resubstitute is u. So we need to resubstitute u back into the equation. So 1/12 u was x squared minus 1 to the sixth plus c. So that's our final answer for the integral of that function right there. If you want to double check to see that we did set up this problem right, we can take the derivative of this and we should get back to the original function. So if I do the chain rule, I would multiply 6 by 1/12 and get 1/2, and then I'd have the inside of my function left inside that group, reduce the power of 6 by 1, and then multiply by the derivative of the inside, which is just 2x. And then the derivative of c is just 0, and you can see that this will simplify to be 2. It'll be x, because 2 times 1/2 is 1, times x squared minus 1 to the fifth. So that's our derivative of our answer, which is what we originally started with. Now I'm at 12 minutes, and this thing is a beast. My hope is to do 2 more examples with you. If you need to pause, of course, utilize that. You might have to go back and rewatch some things, and that's all right. But we're gonna repeat this pattern a couple times in the video, and then I've got 4 more for you to try and repeat the same pattern. So I'm actually going to choose a couple here. I'm gonna leave some of these for you to try, but let's do number 1 together. So I'm gonna zoom in. There we go. So we're gonna set up with the pattern that I listed before. So we need to define u, which is the group. What is the group inside? And it's pretty easy to see that 3x minus 2 is inside that something to the 4th power. And then we need to find du. So du over dx is just the derivative of that thing. So the derivative of u is du over dx, and the derivative of 3x with respect to x is just 3. The derivative of negative 2 with respect to x is just 0. So that's going to be our setup for this. But if you remember, we need to isolate du. So du is 3 times dx. And then we can start substituting. We need to make sure that we can substitute everything we see in this integral. So we can substitute this 3x minus 2 for u, and we can substitute dx with almost we can almost do it. So we'll just move the dx, or what's paired with dx away from it. So this will substitute with 1/3 tu equals dx. So we don't want that we don't want this version of the question. Okay, so now we're ready to substitute. So I'm going to write what I'm integrating now. And I'm going to integrate u to the fourth times 1/3 du. And I could also just as easily write this because of the rules of integration. So now I can integrate because this is easy to integrate. I don't have any groups to work around. I can do 1/5 u to the fifth plus c, and then times 1/3. So my final answer is going to be 1/15, whatever my u was, so I'm replacing u, 3x minus 2 to the fifth plus c. So that's my final answer for that problem. That's the answer to my integral problem. Now, I'm going to do, let's see, I'm going to do a rather difficult one here in number 6 so that you can see this and have a full spectrum of things to carry on with. And let me scroll over here. So this problem, it looks really nasty. We could start like doing U-substitution, but we really need to start rewriting this so it looks a little bit nicer, and then we can apply U-substitution. This should be old news for you by now. If something looks nasty, rewrite it first and then start using your methods for integration or derivatives. So that's a -1/3 power on that cube root of 2x squared minus 1 that's in the denominator. Hopefully you remember that from how we rewrote derivatives. Okay, so here we are with the U-substitution process. We're going to claim u, so we're going to define u. So u is 2x squared minus 1. And then we're going to find du. Du is going to be 4x to the first power minus nothing. So it's just 4x. And I'm going to move dx over to the other side. And then I'm going to check do I have a 4x dx in this problem? Do I have a 4x dx in this problem? Well, I have an x dx, so I need to move the 4 away from x dx, and then I'm ready to start substituting. So hopefully you're seeing the rhythm here for this procedure. All right, so now that I can substitute, I'm going to integrate u to the -1/3 times 1/4 du. So I've replaced 2x squared minus 1 with u, and I've replaced x dx with 1/4 du. Okay. Integration. This is an easy integration problem now. I add 1 to 1/3, so it'd be u to the 2/3, and then I divide by 2/3, which is multiplying by 3/2. And then I'm multiplying that by 1/4 because my constant out to the side there can just be multiplied into my answer. And then plus c. Now I can resubstitute what u was into the problem. So this process is, I mean, kind of crazy because the chain rule by itself is a crazy process. But what I really like about it is we can undo operations, and it's really nice to be able to undo something because that means it's really flexible and malleable. So I hope you find some, at least, I don't know, awe in that we're able to do or complete some math that's at this level, because it is difficult. So we'll be practicing this a little bit, and we'll be talking about the answers to this worksheet next time I see you. So I believe that wraps up that problem. Let me double check. I've rewritten, yep, u inside of that, and I did my fractions right. All right, great. So thanks for watching, and I'll see you guys in the next one. Bye.